Hey, hey, ha. You recognize that one? Hey, ha. Chinese. Hi, how are you? That's Chinese for come on, stop. So who's ready to learn more about electric circuits?
How's Geese quiz?
Yeah.
Bill, I forgot we were going to have one. So I didn't study. Do what?
I didn't read it yet. I just wrote down every one that I know.
Right? Are they? Well, overall, if you pull that right,
Yeah, that's what it was.
I wrote down, pastor start, pastors.
I got
Yeah, I got this after.
I put down single phase and three phase also. Yeah, I put it in pickup. And then he said it's always, yeah, I put those four.
I feel like I'm pretty sure the third one was totally wrong.
Well, after I wrote that down and tried it in my test, somebody else asked, so this has to be three-phase motors, right? Not just single phase. He was like, yeah, no single phase. I was like, oh, that's one of my wrongs. It was the quiz for PCB.
Oh, they're all three phase.
Yeah. Yeah.
Did you get signed in? Who has this? You got it? Did everybody sign in? All right. We looked at resistors and how they go together in series and in parallel. Today we're going to look at capacitors and how they go together in series and in parallel. And we put these three capacitors all in parallel tied to this battery. That battery with that voltage is going to push out some total Q charge. It's going to push out some total Q, total amount of charge. It's going to equal however much charge equal the sum of those three individual charges. So that Q total will equal Q1 plus Q2 plus Q3. And you might notice that I'm using three of them and not just two because, well, we saw last week that if you just use two, then you can get some interesting, but not really relevant results. We're looking for a more general case. Now, we know that the total Q that it puts out, that the battery supplies, is going to, am I reading that? Yes, I am. The total Q that it puts out is going to equal the voltage applied, the voltage of the battery, the total voltage, times the total capacitance of the whole circuit. And so what we want to find out is, what is that total capacitance? Well, how much charge is going to be, how much charge is going to be here? We know that the charge on C1 will be equal to the voltage times C1. Right? That's how much charge a capacitor will store. For a given capacitance, you apply a voltage to it, the voltage times the capacitance gives you the total charge. That's true of C1, Q of the first capacitor. The second one, and the third one. So, we replace Q1, Q2, and Q3 here. We end up with Q total equals the voltage total times the total capacitance, which will also equal the voltage applied to C1 plus the voltage applied to C2 plus the voltage applied to C3. Voltage is the same all the way around, so we divide through by voltage total, and we are left with the total capacitance of the number of capacitors in parallel is simply the sum of the capacitors. Capacitors in parallel add together just like resistors in series. So if you put 3 capacitors in parallel, you just add them up and that gives you your total capacitance. Any questions on this so far? How old hat is this for y'all?
It's been
Devices and standards, we did it, right? Again,
4 semesters.
we did it again, and then we did it our second semester in ACDC too. We looked at this. I know it for sure ACDC too. So at least a year.
About 4 semesters.
All right.
It's a very good. It's like bombs.
Yeah, that's the one over the capacitor plus
Yeah.
over.
Exactly. But let's get there one step at a time, because I really do want y'all to see why that is the case. Not just that is the case. Say again?
I don't know, since our professor wasn't commenting.
Well, this time we're going to have to put a little more thought into just exactly what happens. Again, we know that the total charge is going to be the voltage times the total capacitance. But where does that charge go? When they were in parallel, it divided up evenly, it divided up proportionally between the 3 of them. But now, whatever that QT is that pumps out of that battery, it goes right there to that first capacitor. And that's it. It's an open circuit. It's a dielectric. There's no conduction here. That charge can go no further. But what does happen is that positive charge here induces an equal minus charge on this plate. But where does that minus charge come from? Because this whole bit of circuit right here is electrically isolated. No charge can get in, no charge can get out. It starts off totally neutral, so it has to stay totally neutral overall. That means, since that's minus Q, that it induces a plus, an equal charge, positive charge on this plate, which in turn induces a negative charge on that plate that came from this plate that induces a negative charge on this plate that came from right here. Okay, so that is what's different. The total Q, and if you think back a couple of weeks when we did capacitors, the total Q is whatever's on one plate. Not what it's not the sum of the two plates, because the two plates will sum to, if you add all the charge from both plates of the capacitor, what does it equal?
Zero. Because one's positive.
It equals 0. Yeah, exactly. So, the total charge generated by this circuit will appear on each and every one of the capacitors in series. So, what else is different about this circuit? What does Kirchhoff's voltage law tell us about this circuit?
Sum is 0. All three.
That's right. All three of these voltages have to equal the total voltage applied, so that the sum around the loop is 0. So, V total has to equal V1 plus V2 plus V3. Okay? We know the Q on each one of the circuits, each one of the capacitors is Q total. And we know that that will equal the capacitance times the voltage. What is the voltage? How do we solve this for voltage? We want to know the voltage across V1. We also know that the total charge is equal to the second capacitor times the second voltage. And we know that the total charge is equal to the third capacitance times the third voltage. Now we can solve each of these for the voltage. And now we can replace all of these. We know that the total voltage, we can solve for it as the total charge divided by the total capacitance. Well, now we replace these voltages in this equation and we end up with Q total divided by the total capacitance is equal to Q total divided by C1 plus Q total divided by C2 plus Q total divided by C3. Does everyone see where this is going? Divide out the total charge, and we end up with the reciprocal of the sum of the reciprocals. So capacitors and resistors work exactly the opposite. If you put several resistors in series, you add the resistances to get the total resistance. If you put resistors in parallel, you take the reciprocal of the sum of the reciprocals to get the total resistance. With capacitors, you put them in parallel, you add the capacitances to get the total capacity. And if you put them in series, you take the reciprocal of the sum of the reciprocals to get the total capacity. Any questions?
Or you could just do the C1 plus C2 plus C3, then do the -1, right? Like if you had it all in parentheses, put the -1 on the outside of the parentheses, right?
Yeah, exactly.
That's the exact same.
If you take the reciprocal of both sides, then the reciprocal of this is just total capacitance. Just like that. Again, you learn to use the reciprocal key on your calculator and you can do it quick. C1 reciprocal plus C2 reciprocal plus C3 reciprocal equals reciprocal. There's your total capacitance. Just like resistors in parallel. Any other questions? All right, well, then let's start looking at charging these capacitors. How long does it take for that charge to travel down and to find equilibrium, to charge up all of those capacitors? Seriously, how? We hook up the battery and we take these three capacitors, we put them in series or we put them in parallel, either one. Hook them up to that battery. How long does it take before they're fully charged? Voltage is
C times E.
Say again?
That's wrong. Doesn't want E.
Well, we haven't gotten there yet, though. What are we missing? No, each one of these C's, capacitance is specified in farads.
Oh, yeah.
But that charge starts off here. And it has to migrate down the circuit and charge up, which then induces the charge on the other side. So there's a propagation going on here. How fast does that happen? What do we need to know? What do we need to know? We're looking for time. Charge per unit time.
T equals R times C.
What is charge per unit time? Current. What is our total electrical current in this circuit? No, that's the total charge. That's how much charge is gonna move, but how fast does it move? That's the question. What would the current be? Is basically what I'm asking. What would the current be in this? What's Ohm's law tell you? Ohm's law tells you how much current you're going to get from a given voltage on a circuit. Say again?
V over R.
V over R. What's our resistance?
Whatever resistance is in the capacitor. It's non-existent.
Well, pretty close to non-existent. The resistance is the resistivity of the wire times the length of the wire divided by the cross-sectional area of the wire.
So since you don't have a resistor,
It's going to charge just ridiculously quick. And it will probably arc and spark when it does. You know, depending on how big the capacitor is and how much voltage you got. But the current limit on the battery is, because there is an internal resistance in that battery that's going to slow the current down some too.
Isn't the internal resistance just 1 ohm, right? Or does it vary on each battery?
Oh yeah, it varies from battery to battery, depends on the chemistry, on the age of the battery, the condition of the battery, on the charge state of the battery.
I take a guess there's a big formula for that, or
I'm sure there's one somewhere. Yeah. You know, my formula for resistance, the internal resistance of a battery is, if it matters, throw away the battery. In this circuit, what would happen? You hook up this battery, and in that first initial instant that you hook up the battery, this thing basically seems like a short circuit to the battery. So the voltage, the terminal voltage on the battery is going to drop to 0. And the total voltage of the battery is going to be dropped across the internal resistance of the battery. And the current is going to be probably the limit of whatever that battery is capable of producing. And that is what will determine how fast these capacitors charge up. Because in that initial instant, when you first close the switch on this circuit, the voltage across each one of these batteries, each one of these capacitors, is 0. And that voltage then increases as the charge builds up. Right there. When the charge is 0, capacitance is constant. So the voltage has to be 0. As the charge builds up on each capacitor, the voltage across that capacitor increases until the voltage times the total capacitance, or the capacitance of that particular capacitor, is equal to the charge that is developed across it. Once that happens, how much current is flowing? None. One of these capacitors is an open circuit. It's a dielectric, it's an insulator. So once they're charged, there is no current flowing in this circuit anymore. If we were to plot a graph of what that looks like, this is T0. This is the voltage across, say the voltage across the battery. The instant you close the switch on that circuit, this voltage drops to something very nearly to 0. And then
shoots up like a spike.
the current, call this the current, this is the voltage. The current will immediately spike up to some ridiculously high current and then drop off very quickly. The voltage will immediately spike down to 0 and then start to build up. Now, that is what happens if you're stupid enough to just hook up a bunch of capacitors to a battery without any current control. Generally not a good idea.
Would most of them just blow the capacitors if you did that? Or
Something will vary, it depends on how much they can handle, how much stress the circuit can handle. You could design a circuit that would do this, but
you wouldn't want
why? is, this is not a good way to do it. What you would do is you would add the resistor, R. Now, when you first turn on this voltage, this current is going to jump up to some maximum level of V over R. And the voltage is going to drop to some minimum level of, what is I times R. Of course, then at that point, the voltage across each one of these with no charge on them is still 0. So as they charge up, the current will start to drop to 0, like so. And the voltage across the resistor will also drop to 0. Because as the current decreases, the voltage across the resistor goes away. Voltage across the battery goes back up to the terminal voltage. So if we're drawing here the voltage on the battery, and this is what it drops to, and then it will climb back up to the terminal voltage of the battery. Now, there is an equation, a formula that expresses the rate at which this happens. Voltage across the capacitor. Voltage across the That is how the voltage across the capacitor will charge up. How the voltage across the capacitor will grow with time as the capacitor charges. One, initially the voltage at time 0, what is e to the minus t over rc? When t is equal to 0. And t over rc is 0. E to the 0 is 1. 1 minus 1 is 0. So the terminal voltage times 0 equals 0. When you first turn on the circuit, the voltage across that capacitor is 0 volts. The current flows, the charge builds, and the voltage increases according to that equation. Now, right here, this term right here, 1 over RC. Are they saying 1 over RC or this? No, they're saying, okay. RC, the resistance times the capacitance. That is your time constant tau. We're going to go through and look at what the book says about it. But here's what you need to know. It's going to take, in order for that voltage to reach, I think, 95% of the total terminal voltage, or for the capacitor to charge up to like 95% of its total charge, it's going to take 5 of these, 5 time constants. Here, we're also looking at how the voltage develops across the resistor. And they go through a derivation here in the book. If you want to look at it, we can. But voltage across the resistor decays like this. At t equals 0, what is e to the 0? 1. So at the moment you first turn on the voltage, turn on the circuit, you close the circuit and start charging the capacitors, the voltage across the resistor is the total voltage. But it will then start to decrease as time goes on. As time gets larger, e to the 1 over e to the t gets smaller. And so this voltage across the resistor will decay until the capacitors are totally charged, at which point the current is no longer flowing and the voltage across the resistor has dropped to 0. And again, you're going to get to about 95% or so of that in 5 time constants. I take it y'all have all seen this before. You've done the RC circuit.
It's coming back. I don't remember the VR equals VE to the negative T over RC. I don't remember. I don't think we ever did that.
Okay, well, this is a rather complex circuit to talk about it with, so let's simplify this a bit. Just deal with a simple single resistor, single capacitor. That's the switch. When the capacitor is fully discharged, the switch is open, the battery is at terminal voltage, no current is flowing, there's the voltage across the battery terminal all of the voltage is dropped across the open switch. No current is flowing. Actually, it would be dropped from the open switch to here. But you get the idea. What happens the instant you turn on the circuit? Voltage across the capacitor is 0 because no charge is built up yet. So the voltage there Q is 0, the voltage is 0 across here. That means the total voltage the battery, and we're gonna, for this and for our purposes right now, we're gonna ignore internal resistance and resistivity of the wires and all that. The total battery voltage here is dropped across the VR. So at t equals 0, I'm writing this right now. T equals 0, e to the 0, not e to the 0, e to the minus 0 is still 1. So you get your total terminal voltage across your resistor at T0. As current flows, current now will start to flow because, well, it will flow. What will the current be? The current will be V over R. Actually, it will be, well, yeah, it'll be the V over R being your maximum current for that circuit. When the total voltage is developed across the resistor, the current flowing is voltage divided by resistance. That's this. That's your voltage. Here's our current. Now, after a certain amount of time, how is that voltage? The charge starts to build up. Well, this is hard to do without numbers, isn't it? Yeah, without the, I guess they kind of do here. When T is equal to RC, 1 RC, and then, yeah, that's actually a good way to do it. We'll go in terms of number of time constants. When T equals RC, one time constant. What is e to the minus 1? When T is equal to RC, this becomes e to the minus 1. So e to the minus 1 is 0.368. So at one time constant, V total times 0.3 and 0.37. Running out of room. Okay, so 0.37 of Vt, that would be about what here? About a third. What will it be after when T is twice the value of RC, after 2 time constants? Well, e to the negative 2, 0.135. So we're down here now. Okay, at 3 time constants, what's e to the negative 3? 0.05. Now we're here at 95%. So in 3 time constants, we're down to 95%. After 4 time constants, we're down to 2%. 0.18. And after 5 time constants, we're down to half of 1%. Actually, 0.007. So we have lost at 5 time constants, we've changed by 99.3%.
So your first time constant is going to be your highest number you get, correct?
Yeah. Well, 0 time constant is going to be your highest voltage. Current will go the opposite. The current, well, no, actually the current will fall off like this too, because the current will decrease as the
Voltage increase.
as the voltage across the capacitors increase. As Q builds up, current will decrease. Let's look at how the voltage will develop across the capacitor. Voltage across the capacitor will start off at t equals 0, e to the minus 0 is 1. And 1 minus 1 is 0, so at t equals 0, they're right there. At 1 RC, and I should have written these down. In fact, I'm going to write them down this time. Y'all can copy these if you want to. When t is equal to 1 times RC, e to the minus 1 RC over RC equals 0.368 and more. That's rounded. So, this is V total. 0.368 is, you then subtract that from 1. We're already at 63% here. So it's 13.135, and subtract that from 1. And now we're at 86.4% here. Three RC.
Should be at 95%.
Thereabouts, I think, yeah. I don't.
And then it goes to 98, and then it goes to 99, and then it's like 99.75.
Yeah. And that's actually not trivial. In mathematics, never, ever, ever reached terminal voltage. But do you have a voltmeter that can read that?
No.
Yeah. That's why the first thing I wanted to point out to each of you, we're not talking about mathematical and theoretical simulations. If you're actually dealing with voltmeters in the field and capacitors, and you're trying to get the compressor to fire on the AC unit, or you're trying to get the motor to start, 5 time constants and you're done. Okay, you're there. Any questions? There's one more thing I want to talk with y'all about before we go. Did this come up in this? Yeah, I think it is here. And I don't know that any of it is, yeah, 19.8. I don't know that this is actually part of your homework assignment. But that doesn't mean you should feel free to ignore me. Let's see. Yeah, I don't see it as, I don't think your homework goes this here. I think we finished with what where the lesson plan for this course ended with 19.6. But in 19.8, it talks about the effects of ammeters and voltmeters on your circuit. Now, this is a lot less of an issue for you than it was for me when I was getting into this stuff. I grew up on analog voltmeters, galvanometers, resistances, and the impedances that they introduced to the circuit were not always trivial. Okay? If you put a galvanometer in series with a circuit because you want to measure the current, well, then you're literally adding resistance to that circuit. And so if you're doing these measurements and they are critical measurements and you need to be real clear, you will want to figure out how much is your instrument affecting the quantity that you're measuring. The same thing with the voltmeter. There's some finite resistance that you're adding, usually in parallel to whatever it is, the voltage that you're measuring. So if you're measuring a 100 ohm resistor, and you've got a 100,000 ohm voltmeter that you're putting in parallel with it, you're not really going to change it much, but you are going to make it a little bit less than the 100 ohms that it would have been without the voltmeter in parallel. And with the old analog voltmeters, that resistance could be much lower than 100,000 ohms. Depending on the range of your voltmeter that you were dialed into, you were dialing through networks of resistors and things in parallel and series. And you could find yourself putting a few thousand ohms in parallel with a 100 ohm resistor, and then all of a sudden now you're not measuring a 100 ohm resistance anymore. You're measuring a 60 or 40 or 80 ohm resistor. And you would have to take that into account. Of course, nowadays you probably use all digital voltmeters, which means you're talking about 20 mega ohms of input resistance. So you put 20 mega ohms across a 100 ohm resistor or a 1,000 ohm resistor, or you're still going to measure 1,000 ohms. Put 20 mega ohms in parallel with a 1 mega ohm resistor, how much would that affect your measurement? What's 20 ohm? Break out your calculator. So you've dropped your resistance 0.2 mega ohms out of 2 mega ohms. That's a 10% reduction. You just changed the value of that resistor by 10% when you plug that 20 mega ohm. Now, if that circuit was designed around a resistor with a 5% tolerance, you just changed your circuit. So this is something you need to be aware of it, because there may be times when it will matter when you're doing things in the field, even with the new modern, digital voltmeters. There will still be times when it does matter. So, like I said, we're not going to cover that in the. That's not in the homework. It's not going to be on the test, but it is still something I think you should know and be aware of. Go. See you Monday.